So guys, today there's not really a class. It's just going to be a review for the exam. So somebody requested to do out of the assignment 7, problem 1. Let's see what that is. So assignment 5, 6, 6, 6, 6. Let's see what is 7, 7. So again, 434, I guess that's what it is. Okay, so let's work on this problem. So you do the figure, I'm gonna do the figure on my side on this page, and then we see how we can complete the figure in order to solve the problem, okay? But again, we're all gonna have different data, no? I don't even know if this data is correspond to what is gonna be given there. I mean, steam enters the first stage at 40 bar and 400 degrees Celsius. Ah, okay, yeah, they already did a change. Okay, so let's just do the figure. Problem 434. Okay, so I'm gonna stop the recording as I do the figure, and then I will pause it again. So basically, after doing the figure over here, all right, we need to find, looks like the volumetric flow rate at 1. So over here, we need to find AV1. And, oops, that's not what I wanted to do, too late. And we need to find the then step 2. Okay, so I guess we know what step 2 is. One was, oh, okay. We need to find the work, determine the total power produced by the 2 stages. We need to find what is the total power. And part 3, I mean, I don't mind if you see the answer. Personally, we need to, everybody will get different answers. And part 3, what is the amount of heat into the reheater? Okay, this looks like being a good problem. Okay, so over here, first thing we're gonna do is, let's say part 1, or part A, as they call it here, part A. We're gonna determine the volumetric flow rate at 1. Okay, so let's see. I wanna use the blue because it's new, the black is a bit old. So what is the definition of the mass flow? We saw that the mass flow is equal to rho AV, where AV is the volumetric flow rate. And we said that the mass flow is also equal to AV divided by the specific volume, because V is just the inverse of the density, no? Okay? So that's basically the equation we have. Over here. So we need to find AV1 in what units? Let's see, we need to find AV1 in cubic meters per minute. Okay. All right, so over here, do we know, so from that equation, we find out that the volumetric flow rate will be equal to what? The mass flow 1 times V1. Where M1 is equal to what? It's 80,000. Oh, sorry, kilograms per hour. So if we want to transform that per minute, what do we need to do?
Multiply by 60.
So basically 1 hour will be 60 minutes, no? Yeah, and what would be this value then? When you do it for me, so it would be 80 divided by 6, 12, no, 14, 60.
1,333.
1,333. Yeah, 0.333, no?
Yeah.
And this should be now basically kilograms per minute. All right, now we need to find the specific volume. So how can we find the specific volume? We can find it from the tables, no? Yeah, what is the substance? Water. So we know that P is equal 40. So they tell us it's steam, but maybe we can go and check. So here we need to go to the tables. So let me go to the book. I use the 8th edition because it has those different colors. All right, so let's see. I guess would be table A2 or A3. Okay, so let's go over here. They go to table. So let's see, let's go to table A3. I like more table A3, I guess. Okay, so over here, I mean, we could do this one as well. What is the temperature? 400, let's see, we get here to, okay, so we don't have here 400, okay. So let's see, what is the pressure? 40 is 40 bars, so this is in bars. Let's see, we get 40 bars, so 40 bars. What is the temperature? The saturation temperature will be 250.4, no? Yeah, what is the temperature we have? Is 400. So as they tell us in the problem, what is the state? Should be saturated vapor, no? I mean, it should be vapor of gas. So basically we can write over here. What is that, table A3, I guess? So from table A3, you don't need to do that because it already tells us, but table A3, okay, on the exam, I would like to see T1 equal 400, which is higher than the T saturation that is equal to 250.4 degrees Celsius at P equal 40. Okay, so now that means that we know that we need to go to which tables? Table of the superheated, that will be table A4 at P equal 40 and T equal 400. Okay, so table A4, let's see. Table down, so let's see for 40. Hopefully we have 40, we don't have to do crazy interpolations. Oops. Now we're up. 120, 40, that's good. So we have it here, table 40, 400, what should be V1? 0.07341. So V sub 1 equal to 0.07341. And the unit for that should be cubic meters per kilogram. Okay, so let's say we do the numerical application. We're gonna have AV1 equal to mass flow times specific volume. Will be equal to what? 1,333.33 kilograms per minute times V1, which is 0.07341 cubic meters per kilogram. So you see right away that this kilogram will cancel out, and we're gonna get the units that they're asking us. So hopefully when you do this calculation, so do it again and check, but we should get something close to what? 97.88. Is that what you get or no?
Yeah, that's what I got, exactly.
Is that what you get doing that calculation? All right. So 97.88, and the unit should be cubic meters per minute. Which is the value that we had, no? Okay, so let's go to part B. What is part B? We need to find the total amount of work produced by the turbines. Okay, so again, what is the function of a turbine? Is to generate power, no? So the total amount of power should be equal to whatever power generated by turbine 1, plus whatever power generated by the turbine 2, no? So I think in this case, we're gonna have to differentiate two different control volumes. One for the first turbine, and one for the second turbine, okay? And we find what is the work, the power produced by each one of them. All right, so let's do that. Okay, so let's look at the turbine 1. One and 2. So we already know 1 is P1 equal to 40, T1 equal to 400 degrees Celsius, and P2 equal to 20 bars, and T2 equal to 400 Celsius. And this is going to produce power. And I mean, we don't know, we can find M1 easily, okay? All right, so if we do it this way, you're gonna apply now the first principle to this control volume. So let's say here, this control volume here. So for control volume 1, again, I'm going to use the blue because it's brand new, so it writes it much better. So what do you have? We're going to have M1, so sorry, would be Q dot minus power plus M dot 1 H1 would be equal to M dot 1 H2 because it's conservation of mass flow, no? The M would be the same everywhere, no? Okay. So if you want to run here, we have M1 equal M2 equal M3 equal M4, basically, okay? Okay, so in this problem, do we have any heat? They said to assume that there is no heat transfer through the turbines. So we're gonna have that the work of the power generated by the first turbine will be equal to what? M dot 1 H1 minus H2. Okay, so let's look at the value. So what is M dot 1 will be equal to what? We know it's equal to A V. Oh, we already know what it is, no? Sorry. is given to us is 1,333.33 kilograms per minute. Okay, it's given to us. So now, how can we find H1 and H2? So H1, we can go again to an H2. For both of them, I think we could go to table A4, no? So for table A1, we could look at P1 equal 40 and T1 equal 400. What is H1? So H1 will be, same over here, will be 3,213.6. Kilojoules per kilogram, all right? And at P2 equal 20 and T2 equal 400, so I guess this is still, maybe we'll find out of this table. Is this correct? 20 is here. What is the saturation? 212, no? So it's still vapor. And at 400, the H, I think is the third column. Yeah, it's this one. So at 20, 400, we'll have 3,247.6. Okay, so we have the data, but maybe we can do everything together. No, the final application we do it at the end. Or you rather calculate now the work for one. I mean, let's do it now. So numerical application, power of the first turbine will be equal to what? 1,333.33 kilograms per minute. Times we're gonna have to do some units transformation. I'm guessing times H1 is 3,213.6 minus 3,247.6. This is kilojoules per kilogram. And they want the power in what units? I think they're gonna want kilowatts, but yeah, kilowatts. Okay. All right, so do this calculation because I'm not gonna have space here for the.
Kilowatts is per hour, right? Kilojoules per hour?
It's kilojoules per second.
Oh, per second.
That's why we're gonna have to transform those minutes into seconds. I mean, since you mentioned it, maybe.
So I got negative 2,700.
So this should give you. So this gives you here 2,700.
Well, so with the minutes, it was like negative 165,000.
Okay, so hold on one second. So here you already did this then. This.
Yeah.
You did the 1 minute equal to 60 seconds.
So that gives me negative 2,755.
Okay, let's see what they got here. So it should be in kilowatts. No, we should get about 1.733, not even close.
Oh, because this is just work one.
Oh, this is just work one, you're correct. So yeah, correct. So this should give you, so give me decimals, okay? Don't round off because otherwise we're gonna end up.
I got negative 755.55.
What about somebody else?
Negative 2,000.
Okay, so can somebody redo this, okay? Let me pause. All right, so let's do the same thing now for the other turbine. Okay, so for turbine 2, okay, guys, one good observation, I didn't pay attention. So this is kilojoules. This kilogram cancel, so it's kilojoules per second. So this should be already kilowatts over here. All right, so let's remove this one. This should be here. All right, so let me scratch this one, and just at the end we have 700 minus 755 kilowatts. Okay. So now we do exactly the same thing for the other turbine. Turbine 2 between 3 and 4. So at 3, we know P3 equal P2, so that would be 40. And obviously this one is going to be even more saturated vapor because it's 500. And we know here is saturated vapor at a pressure of 0.6 bars. So we follow the same reasoning. We say for control volume 2, we're gonna have Q dot minus power 2 plus M dot 1 H3 equal to M dot 1 H4. We know is adiabatic, so this is 0, so there is no heat transfer. So as before, power of 2 will be equal to M dot 1 of H3 minus H4. Okay, so we're gonna add what? P3 equal 40 and T3 equal 500. We're gonna find H3 and at P equals 0.6 and T equal, oh, we don't know. Okay, but we can't find the temperature, no? We don't need it because we know some of the saturation. We know it's saturated vapor. Okay, so we go to the table over here. So we go at 40, which is the one we had before. 40 and 500. This time this should be 3,445.3. 3,445.3. And now we need to go to the 0.6. I think I saw before. Hopefully we have it. But we can find this one from either table A3 or table A4. If we don't have it here, 0.7. Hopefully we have 0. Oh, we don't. Oh, we have 0.06. Okay. We have it in the table A3. Okay, good. So I was going to tell you, let's go to table A3. Maybe we're lucky. So table A3, we have here. So table A3 for this one. So hold on one second. Let me go back to this one over here. So for this one, we're going to use table A3. At P equals 0.6. What do we have? We know the temperature, but we don't need it. It's 86.94. And we're looking for what? We know it's saturated vapor. We're looking for the H sub G, no? Which will be then 2,653.5. 2,653.5. Oops, I did not resume the video, guys. So let me go very quick. Somebody asked me to redo this problem by now considering this control volume instead of two ones. And following exactly the same procedure, I write the first principle of thermodynamics for that control volume. And you see basically that we get exactly the same thing. This term will be the expression we got for the previous work over here, work one or power one, which is here, H1 minus H2. And the second one we got is H3 minus H4, which is exactly what we got over here. So you can expect to get exactly the same answer. So now the last thing we need to do is we need to look at the reheater and see what is the amount of Q that is going in. So now in this case, what do you think would be your control volume? Should be the reheater, no? Okay. So now let's say to solve for Q dot, we're gonna take the reheater as our control volume, and that's between 2 and 3. We have Q. So we know here P2 is 20, T2 is 400, P3 is equal to P2, but the temperature now will be 500. So we have, again, now for this control volume, for control volume 4, Q dot minus power plus M dot H2 will be equal to M dot 1 H3. So in the reheater, you see everything comes from the figure. Is there any power generated by the reheater? No? So we're gonna get that Q dot will be equal to M dot 1 H3 minus H1.
H2, right?
H2, yes. H3 minus H2. So again, it's the same numerical application. Q will be equal to 1333.33 kilograms per minute. I mean, it's the same thing as the other one. Let's see what we had for H3. What was H3? 3,467.6 minus H2. That is, let's see how H2 is 3,247.6. kilojoules per kilogram, and we need to transform that into kilowatts. So again, we're gonna have the 1 minute 60 seconds. And now this should give you Q in kilowatts. And go ahead and check, but hopefully we get something close to, I mean, we should get About 4,888. Is that what you get?
Yep.
All right, so 4,888. Okay, guys, so you see it here that my intuition at the beginning was wrong. I thought that the work of the turbine 1 should be positive, okay? And the work of the turbine 2 should be positive, but I kept going with the procedure, and at final, I realized that actually the first turbine is getting power from the second turbine, no? So you see that if you follow the math and the procedure, you're gonna get the answer.